Yeah, I'd like to pick up where we left off last time and work with you on the remainder of the questions on the practice exam 3. I believe we finished with number 11 and we're ready to do number 12. So number 12, as 2 moles of some acid HA and 3 moles of its conjugate base, A minus, says NaA, but we don't care about the sodium, it's a spectator ion, in volume is equal to V. We don't know what the volume is. And it says if the pH is equal to 4.66, what is Ka? Okay, let's fix it so you can see a bigger rendition of my work area. So this is the problem we're trying to work. 2 moles of HA. The relationship between concentration of acid and concentration of base and pH is the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the A minus concentration divided by the HA concentration. Now, we weren't given concentrations. We were given in number of moles. But I can write the concentration of A minus, is going to be equal to moles of A minus is 3 moles, divided by the volume, V. And the concentration of HA, likewise, is 2 moles in that same volume, V. So when I put this data into the Henderson-Hasselbalch equation, the pH we observe is 4.66. So that's going to be equal to the pKa plus the log. Now, the A minus concentration is 3 moles divided in V liters. And the concentration of HA is 2 moles in V liters. Now you can see in this complex fraction, the volumes are going to cancel out, so it really doesn't matter. We don't need those. So the pH is 4.66 is equal to pKa plus the log of 3 divided by 2. Now, we can do that on our calculator. I turn it on and clear the screen. I want the log of 3 divided by 2. Yes, okay. And that comes out to be 0.1761 essentially. So this number is 0.1761. Now, let's continue to solve for this. So 4.66 is equal to minus the log of Ka, that's what pKa is, plus 0.1761. All right. Now, I'll subtract 0.1761 from both sides, so minus 0.1761 here. And so I take 4.66 minus the answer that I have on my screen is, so I'm coming out with 4.484 essentially. If you can see the calculator, you can see it's lots of digits there. Okay, it's equal to that minus log of Ka. Now, if I multiply through by minus 1, then the log of Ka is this. And to get rid of the log, we raise something to a power. So if I raise 10 to the log of Ka, that gets rid of the log. That's the mathematical equivalent of saying, what is the name of the person whose name is John, right? So it's Ka. So Ka is going to be equal 10 to the minus 4.84. I've got 4.484 rather. I've got that number on my screen, so I'm just going to say second 10 to get to 10 to the x, negative second answer right. Now, that should give me the number I need. So the Ka is 3.28. 3.28 times 10 to the negative fifth. Okay, so that should be the answer then to number 12. And 3.28 times 10 negative 12 is D. So let's go back over and get the next question and put the exam so you can see a big copy of it. And you can see we did get the correct answer, 3.28. 3.28 times 10 to the negative fifth. All right, now let's go on to number 13. Number 13, it says you're given formic acid and we're given a concentration. So I'll write down the data, the HCOOH, and the Ka is 1.8 times 10 to the negative fourth here. And we want to know the volume of 0.0642 molar NaOH required to reach the equivalent point. If you use 25 milliliters of 0.1065 molar NaOH. Okay, all right, now let's pull this over so you can see my pad a little better. So these are the data. Now this is a reaction, and we're going to react NaOH and formic acid, and we're going to make sodium formate and water. Now this is a reaction that's actually going to take place. Now, but the problem wanted to know what is the volume to reach the equivalence point. So if I'm looking at this reaction, it'll take 1 mole of the hydroxide to react with 1 mole of the acid. That's the stoichiometry of it. So the volume of the base times the molarity of the base will have to equal the volume of the acid times the molarity of the acid when we get to the equivalence point. So the volume of acid times molarity of the acid will equal the volume of the base times the molarity of the base. Now, the acid, we had 25 milliliters, no, I'm sorry. Yeah. I think I copied some data wrong. Let's look back up here again. I'm doing number 13. And let me check the data again because I'm looking at something wrong. Oh, it's 25 milliliters or 0.1065. This is formic acid. Okay, all right. So the volume of the acid that we have is 25 milliliters. And the molarity of the acid is 0.1065. That has to equal the volume of base, and that's the point of the problem, times the molarity of the base is 0.0642. And so if I divide by the volume of base, I divide by 0.0642 to get it by itself. So the volume of the base that I'm going to use is 25 times 0.1065 divided by 0.0642. And now that should give me the answer to number 13. So if I take 25 times 0.1065 and divide it by 0.0642, I should be coming out with 41.47. So the volume of the base to reach the equivalence point is 41.47 milliliters. And let's go back and look at our exam again and see if isn't the correct answer. Yeah, there we go. That's response B. All right, so we've got the this particular problem, and if you look down below, you're going to see all of them using this same kind of an example. Same volume of the same acid, same molarity of base, and then we're going to do some essentially titration curve for that. And it's good to do it this way because one thing, it gives us the full titration curve for a single substance. But the other thing is it allows us to use some of the previous answers to begin the next problem. So it saves us a lot of time doing that, but it is going to mean that you're going to have to be very careful and not make mistakes as you go along. Lord knows I make plenty of them, so you can see how I react to them when I do. All right, so let's go to number 14. Number 14 now, what will be the pH of that 25 milliliters of formic acid when titrated with NaOH when 20 milliliters of the NaOH, whoops, I'm at 15. I'm supposed to be at 14. That thing jumped on me. There we go. This is the one we want to do. We want to know the pH of that before any base is added. So before any base is added, all we have going on is the hydrolysis of that weak acid, HCOOH. It's going to dissociate in an equilibrium to H plus HCOO minus. Now it's this proton here is the one that comes off to make the H plus here. So this hydrolysis is going to take place. I'm going to write it like this because this is a setup we can use over and over again in these kinds of problems. So we're going to start out with some initial concentration of this, and none of that's present. So that's a 0 and that's a 0. But then the equilibrium is going to shift to the right. Le Chatelier's principle says you're going to build up anything that's missing in the equilibrium. So it's going to shift to the right. It's going to be X moles per liter of that and X moles per liter of that. And it's going to lose X moles per liter of this. So C0 minus X is going to be the concentration then of this. And then the Ka is going to be equal to this times this, X squared, over the undissociated acid concentration, which is going to be C0 minus X. And if I'm solving for X squared, I'm going to wind up with a solution is that X is plus the square root of C0 minus X times Ka. Now I wrote it like that because I want to use this kind of setup for several different kinds of problems. All I'm going to need is the initial concentration and the Ka. Well, this particular problem, we know the Ka. The Ka is going to be 1.8 times 10 to the minus fifth. I need to get so you can see my pad better. All right, there we go. So here's the setup. This is a reaction that's taking place. C0 minus X is the equilibrium concentration of the formic acid. X and X is the equilibrium concentrations of hydrogen ion and formate ion. Ka is X squared, this times this divided by this. And solving for the X in the squared term, I get this expression. So now all I have to put in is the initial concentrations and we'll go from there. Well, the initial concentration of the acid is 0.1065. So let's then see what it would be if we start this off with 0. So X is going to be equal to the square root of 0.1065 minus 0 times 1.8 times 10 negative fifth. So I'm just, if I put my parenthesis in, so it's just going to be this times this and then take the square root. So let's do it. So I've got 0.1065 times 1.8 with an exponent that's minus fifth. I get that number. Now I'm going to take the square root of that answer. Second square root, second answer is. So what I got, if you can see my screen, what I got is I got 0, x1 is going to be 0.00138 and a whole bunch of other digits there. So that's my first approximation for the hydrogen ion concentration. Now I need to put that in, subtract it from 0.1065. I'll make a point right here. You see this first digit is going to be subtracting from that one right there. That's actually already one significant figure further than we need to our problem. Our constant's only got 2. And so I'm betting when I put this number in and get a second approximation, it comes out pretty close to that same number, 0.00138. So let's do that. X2, now that's going to be, this is 0.1065 minus the answer that I have on my screen, this number here, is this. Now I want to multiply that by 1.8 with an exponent of minus 4. Oh, I put in a fifth up there. Oops. Oops. Let's back up and punt. My first answer is going to be wrong, and I'm going to keep on doing it, and my pH is going to wind up wrong if I do that. So let's back up and punt. Here we go. We're still at 14, and it's X is equal to plus the square root of the original concentration of acid was 0.1065 minus X times Ka is 1.8 times 10 negative fourth. That's what the data says. Okay, now back again, let's put in now a 0 here, and let's see what we get. So I take 0.1065, clear off all of that stuff there. Okay, 0.1065 times 1.8 with an exponent of minus 4. That's this number. Now I take the second square root of that answer, and I get 0.0043784. 4378. Now that's my approximation. Now I'm not so sure. See, I've got 0.004, so I'm going to be subtracting off still in that third decimal place, but it's a significant amount. So let's go back in and see what we get for our second approximation when I put that number back in. So that's X1. My second approximation is going to be 0.1065 minus the answer I just calculated is this. Now I'm going to multiply that times 1.8 with an exponent of -4th. I'm going to get that number. Then I'm going to take the square root of that answer to get the next approximation. So 0.004287. Okay, well, now this one actually is rounding off in the second place, but I would rather have everything locked into the third place so that I know that I'm beyond that the answer I've got is not plus or minus 1 in the last digit. I want it to be exact as I can get it. So I'm going to put this back in, and it's really easy to do on your calculator. All I got to do is 0.1065 minus the answer I just calculated equals, that's an important step, times 1.8 with an exponent, that's -4, equals. And now I want to take the square root of that answer. And let's see, this time I'm getting 0.004289. Okay, now if I'm looking at this, these both would round off to the same number in the third significant figure. And we only have 2, so we ought to be good with this number. So I'm going to say the hydrogen ion concentration in this problem is this. And we need to get the pH. So the hydrogen ion is 0.00428 is what I've got now, but you know I've got all the digits on there. So what I'm going to do now to get the pH, it's equal to the negative log of my answer. This number that I got on my screen right now. So all I got to do is say minus log second answer is 2.37. So the pH is 2.37. Let's take a look back at our exam and see if we got it right. Hey, how about that? 2.37, that's response B. So we are good. Let's go to number 15. Okay, now the data for this problem, we still got Ka is equal to 1.8 times 10 negative 4. pH after 25 milliliters of formic acid when titrated with NaOH when 20 milliliters of 0.0642 molar base is added. So again, our reaction is going to be HCOOH plus OH minus, and that's going to go to HCOO minus plus water. Okay, let's give you a little better view of my screen over here. And now, get all this stuff out of our way. Now, we're going to add some acid and base. And so here's what we're doing. We wanted 20 milliliters. The molarity of the HCOOH given in the problem was 0.1065. the NaOH was 0.0642, and the we've added 20 milliliters of the base. And what we want to know is what is the pH. All right, so there's the problem. Now, here's what we're going to do. I'm going to look at this and say, okay, before this reaction has taken place, I had 25 milliliters, and the molarity of it was 0.1065. And I'm going to add to that 20 milliliters, and the molarity of the base was 0.0642. I know that's getting messy. I'll clean it up right here below you. But if I multiply 25 times 0.1065, that's the number of moles of this acid that I have. So let's do it. 25 times 0.1065. I had 2.6625 millimoles of this acid before it reacted. I had 20 milliliters, so it's 20 times the molarity is 0.0642. I'm going to add to that acid 1.284 millimoles of that. Now, I'm looking at these two concentrations and amounts, and this is the limiting reagent. And this reaction is going to go until all of the NaOH is used up. So what's going to be left? Well, I'll have 2.6625 minus 1.284 moles of this. So that's going to be the number of moles of the acid that I'll have left over when the reaction is done. When this is all reacted, there won't be any NaOH or hydroxide left. It'll be used up. Remember, this is not an equilibrium. It goes to completion. So how many moles of formate will I have? So my HCOO minus is going to be the same as the number of moles of base that I actually used here. So it's going to be 1.284 millimoles of that. Now, I've got an acid and its conjugate base. This is now a buffer. Its pH is going to be equal to pKa plus the log of the formate ion concentration divided by the acid concentration that's present now once this reaction has taken place. Now, we've had 25 milliliters of the acid, and we added 20 milliliters of the base. So now the total volume right now is equal to 45 milliliters. We're going to take that into account, but right now I want to just show you the setup. So pH is equal to minus the log of the Ka is 1.8 times 10 negative 4 plus the log, and now it's the formate ion concentration is 1.284, and it's going to be in a volume of 45 milliliters. So that's going to be its concentration. Now, if I put the concentration of the acid, let's go ahead and do this subtraction. I've got this 1.284 on my calculator screen. So I'm going to take 2.6625 minus that answer. That keeps me from having to write it back in. That gives me 1.3785 millimoles, again in 45 milliliters. So what I wanted to show you is I didn't go ahead and do that division because I knew ahead of time that the volume was going to cancel out down here. So I don't really have to do that division. That saves me a step. So all I got to do now is do what it says there. The pH is equal to, push this up here, pull my calculator over here where maybe it is important that I see it. I'll give you the answer if you can't read it. Okay. So it's minus the log of 1.8 with an exponent that's minus 4. I need to close that parenthesis. Plus the log of, left parenthesis my calculator puts in, 1.284 divided by the answer I've still got on my screen, second answer, and then close it. And that way I didn't have to retype that number in. Okay, so if I didn't make a mistake, I should get the correct pH. pH, according to my calculator, is 3.7138, da, 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 da. So this is the way we would report it. And I don't know whether I've told you this or not, but I will remind you that when we did this calculation, let me do a second 10 to the second answer. The no. It's second 10 to the minus 3.71. That's going to be the hydrogen ion concentration. The actual hydrogen ion concentration, if we calculated it, would have been 1.95 times 10 negative 4. Now I want to show you, if I take the log of this to get the pH, if I take negative log, it would be negative log of 1.95 minus the log of 10 to the negative 4 would be minus a minus, would be a plus 4. No, plus 4. So if I took negative log of this, I'll get a fraction that I'm going to, it'll be a negative number, and I'll get a fraction to subtract away from 4. What the point I'm trying to make is this 3 actually came from the exponent. So when you're taking a pH, you write down 3 digits, but these are the significant digits. This is only 2 significant digits. So be very careful about that. I'll bet Dr. Somebody you have in quant, whose name I will not mention, will probably try to trick you up on that. So remember, the number of significant figures in a pH is not the digit in front of the decimal. You don't count it, whatever it is. It could be 12.31, you know. You still wouldn't count the 2 digits in the 12 as significant figures. You'd only count the 0.31, two significant figures. So in a pH, the number of significant figures is just the number of decimal places. Okay, all right, that's all aside and good. Let's do number 16. Number 16, and I need to put it where you can see it. So I'll share it with you. And we're back. Number 16. Given formic acid, what will be the pH when 25 milliliters of that is titrated when half the volume of NaOH to reach the equivalent point has been added? So again, we're going to have HCOOH. It's going to react with OH minus. And we're going to wind up with HCOO minus and water. And I want the pH at V equals 1/2 equivalence point volume. Okay, now let's somewhere back earlier, that equivalence point volume was 41.47. We don't really need to know that, but I want to set it up. pH, we're going to add some base to it, and we're going to use the Henderson-Hasselbalch equation. Let me get this so you can see a bigger vision of my pad. So we're going to use Henderson-Hasselbalch. pH is equal to pKa plus the log of the HCOO minus concentration divided by the HA concentration. I just showed you a moment ago this is moles as well. So let's suppose I put in, let's say C0 is my initial concentration of my acid. And what I'm going to do is I'm going to react half of that, half of the equivalent of that, half C0 of base is going to be added. So it's going to be half of the amount it would take to titrate that to completion. That's what I'm getting at. So let's look at that and put these in now, and you'll see pH is going to equal to pKa plus the log. Now what's going to happen? This is going to be 0, and this is going to be half C0. Again, divided by the volume, but we know that's not going to matter. So the HCOO concentration, this is all of it minus half of it is half of it. 1/2 C0 again. So this concentration is 1/2 of the initial concentration. And this one is 1/2 of the initial concentration. This is going to divide into this. This is going to be a 1. The log of 1 is 0. So the pH is equal to the pKa at 1/2 the volume to reach the equivalence point. Okay. So that gives us then the pH, and that tells us how to get the pKa of the acid. We can titrate it and then read the pKa. I think what I would like to do here is go back and sort of put a graph down, and we're going to calculate all of these points during this session. We're going to mark pH against volume of base. Okay, and I'm going to go all the way out here, and the equivalence point volume we need to add was 41, I wrote it down a minute, 0.47 milliliters. And we've already calculated the pH before any base was added. Let's see, almost that. Yes. That was, okay, that's the one we just did for 14. At number 14, we found that value to be 2.37. So there's the pH at that point. Now right here, we're calculating the volume to 1/2. In this case, it's 41.47. 47 milliliters, half of that. And we know the pH is equal to the pKa. So if we go back up here and do that calculation, minus the log of 1.8 with an exponent of -4, that's 3.74. So that should be the correct answer for that one. So at 2.37, when we get to here, half equivalence point, that's going to be 3.74 pH. So we've got this point, and now we got this point. We'll add the other points and as we go along. So if we go back and check our answers on this one, I think we got it right. Yeah, this is response A. Number 17. Given the formic acid, same constants, same amounts, and all this, when we've added enough base to get to the equivalence point, what would be the pH of that solution? Now, again, here's what we're going to do. We're going to do the same reaction, pH at equivalence point. Let me pull the screen up so you can see my pad better. HCOOH, still the same reaction with NaOH. And what we're going to get is the HCOO plus water. Don't really care much about that right now, but I'll fix this for you right now. So this is a reaction that happens. Now, when we've added enough base so that the volume of the acid times the molarity of the acid is equal to the volume of the base times the molarity of the base, we've had equal amounts of these added, equal moles. So the concentration when this reaction is done is 0. Concentration of hydroxide is 0 from this. So what are we going to do? We're going to make HCOO minus, and now that's going to have a concentration, okay? The volume of acid and molarity of the acid is usually the ones that we are given easier. So we had 25 milliliters. So this is going to be the moles of this. The moles of this is the same as the moles of either one of them. I'm going to use this one. So it's HCOH is 25 milliliters times 0.1065, 0.1065. It's that many milliliters. And now it's going to be in a total volume. Okay, now what did we add? We added 41. I wrote it down right there. We added 41.47 milliliters of base. So the total volume is now 25 plus the 41.47 milliliters. So the concentration of this is just going to be 25 times 0.1065 divided by left 25 plus 41.47. So if 25 times this is the number of moles, total volume is 25 plus 41.47. All right, so that's got to be wrong. 25 times 0.1065 divided by left parenthesis is 25 plus 41.47. I think I forgot to close the parenthesis. Now that looks more right. So this comes out to be 0.04 0.005566 moles is a molar is what I'm getting. So now this is going to hydrolyze. It's a base. So I've got HCOO minus. It's going to react with water. It's going to give me an equilibrium. It's going to give me HCOO H plus OH minus. So that's the reaction that's going to be taking place. And I'm going to start out with essentially 0.040 other digits, molar this. I won't have either one of these. Remember now, water isn't a reactant, it's a solvent. So when I put aqueous in there, I just needed to show you where the hydrogen ion is going to come from, where the hydroxide is going to come from. It's going to come from the water. It wouldn't be in the equilibrium constant anyhow. So this is going to make X of this and X of this, but now notice X is hydroxide now. So this is 0.040 minus X is the concentration of this. Now this is a base equilibrium, so it's Kb is going to be this concentration times this one, X squared, over C0 minus X to the first power. And so this is my expression that I would need to solve. Now, let's do what we did before. We're going to say X is equal to the square root of C0 minus X times Kb. What's Kb? Kb is Kw divided by Ka. Remember, Ka times Kb is Kw. And we don't need to do that here. Okay? Now, so I can do my math. My first approximation for my X is going to be the square root of 0.040 minus X times 1 times 10 negative 14 divided by the Ka of this acid is 1.8 times 10 negative 4. Now let's go ahead and do this on our calculator. So I'm going to put in a 0 here. So it's just this times this divided by this. So okay, in fact, I've still got my answer on there. Yep, there it is. So that times 1 with an exponent of negative 14 divided by 1.8 with an exponent that's negative 4. Okay, and then I take the square root of that answer. And I get my X1 is going to be 1.49 times 10 to the minus 6. Now here I know when I subtract this from 0.04, 4 times 10 negative 2, and I'm going to take 1.49 times 10 negative 6 from that, it's going to be the same thing. It's essentially no change. So this is going to be the final answer. You could put it back in and try it, but you'll see that's true. Now that's going to be the OH minus concentration. So all I got to do now is I'll give me some white space over here. The POH now is going to be minus the log of the OH minus. And that's going to be my answer on my screen. So POH is minus log of my answer. So if I do minus log of the answer, I get 5.83. And the correct answer should be pH is equal to 14 minus POH, So it's 14 minus that answer. So 14 minus that answer is 8.17. Okay, so if we go back and check and see if that's what we got A. It is A is the correct answer. Okay, so now let's go back to what our titration curve looks like. When I get over here to 41.47, we'll make a dotted line up like this. And if this is like 3, we're somewhere around 8. This point right here now is 8 point, what did I get, 47? No, 8.17. 8.17. So I've got 3 points on my titration curve. Now, let's go ahead now and do the next problem, which I think is going to be the last one on the titration curve probably. And we're up to number 18 now. Okay, so what would be the highest possible pH when 25 milliliters of my formic acid is titrated? So the maximum pH. Okay, and I've titrated with 0.0642 molar OH minus ion. So after we pass the equivalence point, we're just going to have excess OH minus. And if I plugged in the numbers, I could put in the volume of base that I've added times the molarity of the base. Now my acid would be the limiting reagent. Subtract out all of those two, and I would get the concentration of hydroxide ion. And then I just take the negative log of that, and that would give me the values past the pOH. Now that goes so fast that it's going to jump about 2 pH units from 1 drop or so before the equivalence point to a drop after the equivalence point. You're going to have a jump of probably 3 or 4 pH units. So it's going to be very steep there, and it's going to level off at this. Now, if I'm, it's hardly worth it, but I'll give you my screen. When you react the acid, any acid, this one, I'll just write HA and OH minus like that, and you're going to get a large excess of this. Then you're going to have a few moles of this taken off, but a lot of this left over. So the pH maximum is going to be equal to the pH of the OH minus titrant. What you've added to do the titration. So in this case, the pOH in this case, limit, is going to be minus the log of the OH minus concentration. And if it's the maximum concentration OH minus could ever be is what it was to start out with. It's 0.0642. So the pOH limit is going to just be minus the log of 0.0642. That's equal to 1.19. And the pH limit is going to be 14 minus pOH, or 14 minus 1.19. So 14 minus my answer is 12.81. And if we go back and check our answers, that will be correct. Okay, so there we are. Now, before we go on with the others, let me complete our titration curve, because now we've got the data that we can use to titrate it. So if I go across here like this limiting pH was 12.81. So here's what's going to happen. The pH is going to look like this. It's going to go all along here like this. And then when we get to here, it's going to shoot almost straight up like that. And then it's going to level back off to that right there. So that's what the titration curve would look like. And gathering these 4 points allows us to sketch any acid-base titration curve that we want to sketch. So that's really helpful. All right, so now let's go to number 19 and let's see what we've got. And we're looking at it, so let's pull it up where we can see it a little better. At the cursor over here. There we go. Now I've got an equilibrium, and it's actually a Lewis acid base a complex ion formation reaction. But we're just looking at Le Chatelier's principle, and we're trying to predict the effect adding water, adding cyanide, sodium cyanide, or increasing the temperature would have on this equilibrium. So let's, I'll copy it over Cu H2O 6 2 plus 6 NH4 OH sets up an equilibrium of Cu NH3 6 2 plus 12 waters. Now it's also told me that delta H is greater than 0, which means it's an endothermic reaction. So I'm going to put the heat is a reactant. You have to put some heat in when this happens. So that's a reaction. It's endothermic. So now let's get back over here to our screen, and we're going to, number 1 is we're going to add water. Number 2 is going to be we add sodium cyanide. And number 3 is increased temperature. Okay, so now let's go over so you can see my pad. And so these are the things we're going to do to this equilibrium. So let's just take them one at a time and see what they would do. What we want to know is effect on pH. So the effect on pH when we add water. Okay, well, if I'm going to look at this, I'm going to say, okay, if I add water, what's going to happen to that system? And I'm going to dilute everything that's present in there. And now, if I added water to that system, I'm just going to dilute all the concentration. So I can imagine, I don't know what it is, it wasn't given right there, but I can imagine it's a pH. And let's just say if I'm talking about pH, I'm talking about like an acid dissociation type. So what would happen if you add water to something that's acidic? Well, you add water, it becomes more basic. You dilute everything. So when I add water to that, the pH is going to go up. So certainly it's not going to involve number 1. So if I had answers down there, I guess I'm looking at the 3 answers. A does have number 1 included, so it can't be right. It has to be one of the other reactions. And so let's see what happens when we add cyanide to it. Well, now the cyanide ion is going to try to compete with the copper. See, on one side, I've got water, and I've got the ammonia complex of copper. If I put cyanide in, the cyanide is going to compete with each one of them. So suppose it's taking away the ammonia in this product that's got formed when that equilibrium came up. When I do that, it's going to take away some of the ammonia. It's going to cause the reaction to shift to the right. But if I'm talking about this, I just got to know what is the nature of sodium cyanide. So sodium cyanide is a strong basic anion. So this is a base. So what's going to happen when you add a base to anything? The pH is going to increase. So the pH will increase with this one if you add that, because you've added a base to it. And now let's see what's going to happen to the temperature of the reaction. And so if we add the temperature, temperature is a reactant, heat is a reactant, so adding more heat is going to shift it to the right. And so if this thing is sort of basic, shifting it to the right is going to make it more basic, make the pH go up. So I'm sorry, I'm looking the other way around. I'm supposed to be looking at this one. If I'm looking at the ammonium hydroxide, that's where the base is. And if I raise the temperature, I'm going to take away base, make it more acidic, so pH will go down in that one. So that one won't work either. So the only correct answer then is C. Right. And let's see, let's go back and be sure that that's what the equilibrium says. The reaction problem says yes. So C is the correct answer. And again, we've got the same sort of thing happening. Which of these changing will cause the equilibrium constant to increase? Oh boy, that's an easy one, because the only thing that could make that happen is changing the temperature. And now, if the temperature is going to have a reactant here, heat is on the left side, it's endothermic, remember, greater than 0, so heat's on the left. Increasing the temperature shifts it to the right. It increases the concentration of this, decreases these other two concentrations. Since this is in the numerator, that's going to cause the equilibrium constant to go up. So the only one that could affect the temperature is number 3, and that is the correct answer. It does cause the constant to increase. Now, which of these changes would cause the ammonia concentration to increase? Well, they would make the product ammonium complex constant, this one, to increase. Okay, well, now if I put ammonia into water, it makes ammonium hydroxide. So I can look at that, and I know adding more ammonia adds more of this. It shifts to the right. Number 2 is certainly correct. That's going to work. If I add water, I dilute everything, so that's not going to make that concentration increase. It's going to make it go down. What if I add HCl? HCl is going to react with this base. It's going to remove some of it, and it's going to shift it to the left. So the only one that's going in the direction we want to make this concentration go up is number 2. So we're still good there. Let's look at number 22. And we're looking at solubility product constants. And so let me gather the data. I am going to have to work on the pad on this one. We got mercury 1 chloride. You have to know that mercury 1 chloride has a formula Hg2Cl2. Mercury 1 ion is Hg2 plus 2. And we were told that solubility, dissolved moles per liter dissolved, is going to be equal to 7.05 times 10 to the minus 7 moles per liter. Okay, so let's get our screen over here. Now, here's our salt, Hg2Cl2 solid is going to dissociate into water to Hg2 plus 2 ion, aqueous, plus 2 Cl minus, aqueous. So if I'm looking at this and say, well, S moles per liter of this dissolve. So S moles per liter goes this way. So I'm going to get S from here, and I'm going to get 2S, twice as much, of the chloride ion. Now the KSP for this compound, the KSP, is going to be this times this squared. So it's going to be the Hg2 plus 2 concentration times the Cl minus concentration, and that's squared. And now let's put in the values here. The solubility is S, so I'll get S moles per liter of this. I'll get 2S of this. It's squared. Squaring this is 4S squared times S. This is going to be 4S cubed. So the KSP I can calculate from just multiplying 4 times the cube of the solubility. So it's going to be 4 times 7.05 times 10 to the negative 7th cubed. So okay, do that. Let's cube it and then multiply it before. So that's what we have to do. So 7.05 with an exponent that's minus 7. Now on my calculator, I don't have a cube button, I don't think. So I have to do up arrow 3. And that'll cube that answer. So I get this part right here is 3.50 times 10 negative 19. I got to multiply that before, times 4. So my answer is 1.40 times 10 minus 18. So that should be the correct answer. And let me fix it so you can see the exam again. And indeed, that's answer C. Now you do notice that I've carried one extra significant figure because I had 3 up here in this solubility, but KSPs are notoriously bad. So it's hard to get really good values because you're trying to make a solid completely dissociate so it's saturated completely. And it takes a long time and it's a very difficult process. So we almost never report KSPs to more than 2 significant figures here. So that's probably a better, more correct answer than what I got, trying to carry it to 3. All right, so let's go to the next one and see what this has to do with here. Number 23. Solubility product constant of cadmium iodate is 2.5 times 10 to the negative 8. What is the iodate concentration in a saturated solution of cadmium iodate? So number 23, cadmium is Cd, iodate is IO3 minus 1. Now, let me get my screen and, well, let's see, we want to know what is the IO3 minus concentration in saturated cadmium iodate. All right, so let me give you my pad again. All right, now I need to get the formula for cadmium iodate. Iodate's -1, so if I can find my periodic table, cadmium is right there. It's in group 2B. Zinc, cadmium, and aluminum and silver only had fixed charges. So cadmium's only +2. So cadmium +2 means there needs to be 2 of those. So that's my cadmium iodate concentration. And we're told that the KSP is 2.5 times 10⁻⁸. Okay, so there we have the answers of the data that we need to get the answer. So cadmium iodate it's going to dissociate to cadmium +2 and 2 iodates. Like that. And we know the KSP, so let's find the molar solubility and just see what we get for an answer going that way. If I have S moles per liter of this dissolved, it's going to be S and 2S. Again, we're going to have KSP is 4S cubed, but now we're interested in getting the S. So I'm going to take S is going to be the 1 cube root of KSP divided by 4. So now the order is important. I have to take KSP and divide by 4 and then take the cube root of that. The KSP is given. It's 2.5 with an exponent of -8 minus 8. I want to divide it by 4. I get this answer. Now I want to raise it to the 1 divided by 3, 1/3 power. That's the way I have to take cube roots. So what I came out with is S is 0.00184 moles per liter. Is going to be the S. Now, the concentration of iO3 minus from what we showed up here is 2S. So all I got to do is take that answer and multiply it by 2. And that gives me 0.00368 and a bunch of other digits. Okay. And let's see if we got our correct answer. We hope so. So here we go. Oh, sure enough, it's B. All right. All right, that's moving right along. 24. Well, what mass of silver? And now we're going for mass. What mass of silver will remain dissolved in 3.5 liters of a saturated solution of silver chromate? Now, so this is number 24. We got A, silver chromate. Chromate is CrO4, 2 minus. So that means silver is always +1. So it's Ag2CrO4 is my formula. The KSP is given at 1.1 times 10⁻12. The molecular weight is given, so we don't have to calculate that out. It's 331.8. And we want to know the grams of silver that is dissolved in 3.5 liters of the saturated solution. Okay, let's get our screen so you can see my pad a little better. Here we go. So there's the data that I need. So again, we're going to have our solution is Ag2, CrO4, one of those two silvers. It's going to dissociate to 2Ag plus CrO4, 2 minus. Okay. And we're given the KSP for that. So I'm going to go for the solubility again. So if S moles per liter dissolved, this will be 2S, and this will be S. My KSP is going to be 2S squared again times S is for S cubed again. So I can now solve for S, and this KSP is 1.1 times 10 minus 12. So S is going to be 1.1 times 10 minus 12 divided by 4, and then take the cube root or raise it to the 1/3 power. So let's do the math. And what I get is 1.1 with an exponent of minus 12. I want to divide that by 4, and I get 2.75 times 10 negative 11. And then I want to raise that to the 1 divided by 3 power. And I get a mistake. I put the constant plus 12 in. So let's do it again. 1.1 second exponent minus 12 divided by 4 is that. And then raise that to the 1 divided by 3 power. And I'm coming out with a solubility is 6.5 times 10 to the minus 5th. Okay, so that looks like a reasonable answer. My Ag plus concentration that's still going to be dissolved is going to be equal to 2S. So I need to multiply that by 2. So I take that answer times 2. And I get 1.3 times 10 to the negative 4 moles of silver ion per liter. Now it asked me for the mass that will be in 3.5 liters. So if I multiply this by 3.5 liters, that's going to give me the moles that's going to be equal to this times 3.5. So I've got that answer times 3.5. That gives me 4.55 times 10 negative 4 moles of Ag plus, of Ag. Now, I want to convert the moles to grams. And the atomic weight of silver given in the problem is 107.9. So I'm going to take that answer now and multiply times 107.9. And I come out with 0.049 grams. And let's take a look and see what we got on the exam. Oh yeah, it's A. So A is calculated there. All right, and moving right along to number 25. given the KSP, and we got the KSP of a silver iodate, AgI03, is equal to 3.2 times 10 negative 8. The KSP for Pb iodate, lead 2 iodate, that's a 2, is 3.7 times 10 to the negative 13. I just noticed on your practice exam that the formula for lead iodate has PbIO3 in parentheses with the 2, and it's got superscripted. It should have been subscripted. That doesn't make any sense. So what I'm going to do is I'm going to add 10 milliliters of 0.0003 sodium iodate, NaIO3, that's completely soluble, is added to 2 test tubes. One test tube, test tube number 1, is 20 milliliters of 0.003 molar silver nitrate. So all I'm interested in is the Ag+. Test tube number 2 is 20 milliliters of 0.003 Pb plus 2. Okay, so that's got all my data, and we want to know, will we have a precipitate in either one of these test tubes? So let's go back so you can see my pad, and we'll work through this. Okay, now, here's what I'm going to do. I'm going to look at this. I'm going to add 10 milliliters of 0.0003 iodate, and that's going to give me iodate in each one of these 2 solutions. One's going to have silver ion, so am I going to precipitate silver iodate when I mix these or not? This one's got lead in it, so am I going to precipitate lead 2 iodate in this test tube or not? So what I have to do is I'm going to do each one of these, the QSP for test tube number 1. And I want to see whether that's going to exceed the solubility product. So what I've got in test tube number 1 is I've got the silver ion concentration now is going to be equal to, now I had 20 milliliters of that molar, so it's 20 times 0.003 molar. But now I've added 10 more milliliters of water when I put the iodate in. So I'm going to have a total now of 30 milliliters. So 20 milliliters diluted to, of this concentration diluted to 30. So let's see what I'm going to have then for the concentration of the silver plus in this solution after I mix them. So it's 20 divided by 30 times 0.0003. Yep. Okay. So this concentration is going to be 2 times 10 to the minus 4th molar in silver ion. Now what would be the iodate concentration? iO3 minus in that test tube. Well, I'm going to have 20 milliliters of 0.00, I'm sorry, 10 milliliters of 0.003 iodate ion from up here. So I've got 20 times 0.0003. No, I'm sorry, it's 10. Iodate is coming from here. So I had 10 milliliters, 0.003 iodate, but now it's in 30 milliliters of volume. So it's 10 times 0.003 divided by 30. 10 times 0.0003 divided by 30. And that's 1 times 10 to the negative 4. Now, the QSP for silver iodate is going to be this times this. So 2 times 10 to the negative 4, 1 times 10 to the negative 4 times 2 times 2, second exponent negative 4. That's going to be 2 times 10 minus 8. Now, the QSP is 2 times 10 to the negative 8, but the KSP is 3.2 times 10 to the negative 8. So it doesn't exceed this value. This QSP is not greater than KSP. So if QSP is less than KSP, no precipitate. All right. So we know test tube 1 does not have a precipitate in it. So that one doesn't. Now what about test tube number 2? What we're doing with test tube number 2 is we're taking PB plus 2 IO3 minus to make our PB IO3 to precipitate. So now I want to look at the QSP for PB IO3 2. That's going to be equal to the PB concentration times the IO3 minus concentration squared. So I need these two concentrations. So let's get the PB concentration. PB plus 2 concentration. Okay, it's the amount of lead in the second test tube. So it's 20 times 0.0003, and now it's in 30 milliliters. Got 10 more milliliters added to it. So my concentration is 20 times 0.0003 divided by 30. That's 2 times 10 minus 4. The IO3 minus concentration is going to be, I had the amount of iodide that I put in is from up here. So it's 10 times 0.0003, way back up here, and divided by 30. So the IO3 minus is 10 times 0.0003 divided by 30. It's 1 times 10 negative 4 in this test tube also. Now the QSP is going to be equal to the lead concentration, 2 times 10 minus 4, multiplied by the iodate squared. And that's 1 times 10 minus 4 squared. So let's do the math. So I've got 1 times 10 minus 4 in my screen, so I'm going to say square that and multiply it by 2 with an exponent of minus 4. That gives me 2 times 10 QSP is 2 times 10 negative 12. Now, that's less than KSP also for that one. So no precipitate in test tube 2 either. So let's go back and see if that's what we are supposed to be getting. Okay, so, oh, I should have got a precipitate there. Let me go back. Let me go back and look at that again. if I got for the lead in test tube 2, it's 20 milliliters of 0.0003. It's now had 10 milliliters added to it, it's in 30. So 20 times 0.0003 divided by 30 is 2 times 10 to the negative 4. That is what I'm getting. I-date is from the first one, 10 milliliters of 0.003, 10 times 0.0003 divided by 30. So 10 times 0.0003 divided by 30 is, oh, this is 10 negative 3. I copied it down wrong. And this is 3. So let's try that again. 10 times 0.0003. Oh, no, I had it right the first place. I look on my screen. 10 times 0.0003 divided by 30. I just divided by 3. No, I was right. That is the correct value here. So I want that squared, square that, and multiply it by 2 with an exponent of -4. I'm getting 2 times 10 minus 12. Oh yeah, okay, that is correct. I just misread. This number is greater. 2 times 10 negative 12 is greater than 3.7 times 10 negative 13. So yes, I do get a precipitate here. Okay, so the test is right. I just screwed up in the interpretation of the numbers that I had. I actually had the right numbers. Okay, and moving right along. 26, you've got the silver chromate precipitate. What mass of silver chromate will dissolve in 250 milliliters of 0.25 molar silver nitrate? So I've got 26. I've got the KSP of Ag2CrO4 is 1.1 times 10 negative 12. Molecular weight of Ag2CrO4 is 331.8. And we've got 250 milliliters of 0.250 Ag nitrate. So I'm just going to look at the silver ion. Okay, now, so let's look at my screen. And here we go. Now, I've got silver chromate. So here I go. I've got Ag2CrO4 dissociates to Ag plus, and there'll be 2 of them, plus CrO4 2 minus. The KSP is, it's going to be the silver ion concentration, and that's going to be squared, times the chromate ion concentration, and we know this number. It's 1.1 times 10 negative 12. Okay, I do know the silver ion concentration because it's coming in from the silver nitrate. So the silver nitrate, silver ion concentration is going to be 0.25. So this 1.1 times 10 negative 12 is going to be 0.25 molar, and that's squared, and times the chromate ion concentration. I don't know what that is, but I can solve for it now. I've got this number, that, so my chromate ion concentration is going to be equal to 1.1 with an exponent of minus 12. I want to divide that by 0.25 squared. And I get this is going to be 1.76 times 10 to the minus 11 moles per liter of silver chromate. And we want to know how much silver chromate will dissolve. That's how much, this is how much chromate ion is equal to the moles per liter of the Ag2CrO4. So that's the amount in moles per liter of the silver chromate that dissolved. So that's how many moles. So the moles per liter of the Ag2CrO4 dissolved or in the solution is going to be 1.76 times 10 minus 11 moles per liter. And what volume do we have? We have a volume of 250 milliliters, so it's 0.25 liters. Liters cancel. So if I take this number and multiply it by 0.25 times 0.25, the number of moles of the Ag2CrO4 dissolved in the solution is going to be 4.4 times 10 negative 12 moles. And if I take 4.4 times 10 negative 12 moles of the silver chromate, and I want to convert from moles of silver chromate to grams, the molecular weight is 331.8. Get up here where you can see it. So all I need to do is multiply that answer times 331.8. And that should give me the number of grams. So I get 1.46 times 10 negative 9 grams. Okay, and let's check and see if that's what we got. All right, so I need to let you see what I'm seeing. Yep, just a minute, honey. So that gives me, yeah, it's response D. All right. The next one, 27. Okay. Okay. What is the hydronium ion concentration of a solution with a pOH of 4.66? Is this solution acidic or basic? So I want the hydronium ion concentration, H3O plus concentration. I want to know what that is if the pOH is equal to 4.66. So I guess what let me get the screen so you can see my pad better. What I'm going to do is I'm going to get the pH first because it's easier to go from pH to hydrogen ion concentration or hydronium concentration. That's 14 minus pOH. So it's 14 minus 4.66. So 14 minus 4.66 is 9.34. Okay, so the pH and the H plus concentration or hydronium concentration is 10 to the minus 9.34. Okay, now you can see already the pH is greater than 7, so that's a base. So I could eliminate, it is basic, so I can eliminate B and C on the answers already. So to get the H3O plus, I just do 10 to the minus 9.34. And so I get 10 to the second and 10 to the minus 9.34. And that is 4.57 times 10 negative 10. So it is basic. And so let's get the answers. So I need to go back so you can see the exam again. And there we are. Okay, so this concludes all of the problems on the practice exam. And I've worked them out in very great detail, and it's taken me a long, long time, but we could have done this in a lot less time if we just were going for the answers. Okay, I hope this helps you a lot, and I wish you the very best on our exam on Monday. Okay, so you have a good weekend, and I'll see you on Monday. Stay safe and be healthy. And okay, here we go. Bye. That's the end of the meeting. It's right there.